Welcome back. In this video, we're going to look at an example that you've already accomplished, and we're going to add to it a torque. Now this example is 617 from the textbook, and it looks like a shaft with two loads acting down on it, causing bending. As you recall from this problem before, it turns out the critical location is where that shoulder is, and the fillet at that shoulder. And so we're going to look at that same location again. Now if this was a shaft carrying pulleys or gears, you'd expect to see both that bending force pulling it down, as well as a torque transmitted between the two locations, either between the pulleys or between the gears. So that's what we're going to do now, is look at this problem again and consider adding a torque. And what that's going to do is provide us an example of this combined loading. Alright, so let's add to this problem a torque being transmitted between F1 and F2, or F2 and F1, it doesn't matter since it's a torque, of 2,500 pound force inch. That is a torque value. And while this load is being applied, the torque is constant. That means it does not fluctuate with the rotation of the shaft. Generally speaking, when a shaft is transmitting a torque, the torque values do not change while within the scope of a single cycle of its rotation. So we'll consider this a constant torque. So let's understand what that means for our location between the two. So we will have now torque values, or shear stress due to torque, equal to TR over J. And we can use either formulation if we like, the simplification, 16T over pi d cubed, or more fully, with the diameter that we have, that's 2,500 inch-pounds times the diameter, 1.625 over 2 inches, pound force inches times inches, divided by pi over the diameter, 1.625 to the fourth over 32. This will give us a value of fairly low 2,967 psi, or 2.97 kpsi. So that's what we're going to be adding to the problem. So from before, if you've already solved this problem, then you know that the ultimate strength for the material of 1040 cold drawn steel is 85 kpsi. The yield strength for the material, this is just looked up, was 71 kpsi. We will want to know what the bending stress was that got us that value. So at the fillet, at the shoulder, the fillet location, you should have found a fully reversed bending stress. Fully reversed of 35 kpsi, which means that our amplitude stress is maximum minus minimum, so 35 minus negative 35 over 2 gets you exactly 35 kpsi, and sigma mean is 0. This is fully reversed stress. So that's the situation we would have had from before. And the only difference now is adding the steady state stress. So our torque values that we are adding to this is sigma A and sigma mean, shear stress A, tau A, and tau mean, where tau A, the amplitude above and below the mean, is 0 since it's steady state, and the mean is the value that it stays at, kpsi, basically constant loading. So those are the only addition that we're going to add to that problem, and we'll see how that carries through. All right, so for our solution process, we know we're going to use the combined von Mises approach, which requires that we need to know any fatigue stress concentration factors. So let's look those up. So we know we're going to need Kf for bending at the fillet, and we're going to need Kfs for torsion at the fillet as well. To get there, we're going to need to know the theoretical stress concentrations as well as a notch sensitivity factor. So 1 plus Q axial, or bending, will be the KT of the bending minus 1. And same thing for shear, except we'll use the notch sensitivity and the theoretical stress concentration in shear. So we can look up Q values and QS values from our tables, depending on the size of the notch. So the radius in this problem is our notch, is 1/16 of an inch. Radius is 1/16. The big diameter that it jumps between is 1.875. The little diameter is what we used before, is 1.625 inches. And we can use these values to find our KTs and Qs in a way that we've done several times now. I'm not going to do that again in front of you since we've done it several times. But if you look up the theoretical stress concentrations from the figures in the back of the book, you'll find KT for bending at a fillet location to be about 1.95, and KTS to be about 1.6. Our notch sensitivities, Q, at this ultimate strength is going to be about 0.76, and our QS is going to be 0.81. Now these are values that I would estimate based on the graph that I'm reading. You may find that your values looking at the graphs might be a little bit different. So don't be surprised by seeing 10 to 15% error in these answers that you get, largely due to the fact that our Q estimates and our KTs are best guesses off of graphs. All right, so now we know our KT and KF, so we can calculate the fatigue stress concentration factors such that we will have Kf in bending. If you plug all those numbers in, you'll get an answer close to 1.72. And if you plug these numbers in for KFS, for the torsion stress concentration factor, you should get about 1.5. I have 1.49. So these are our stress concentration factors, which we'll now use in our von Mises expression. So sigma A equivalent, or von Mises, recall, is the axial portion, so Kf in bending, times sigma A in bending, plus Kf in axial, times sigma A in axial, over 0.85. That all squared, plus 3 times tau A KFS times the shear, and all of that to 1/2. And the mean is the same, except we do not have the division of 0.85. So our simplified version of this, we don't have any axial stress, so that goes away. And recall that our shear stress caused by the torsion is constant, so there is no amplitude. So it ends up that goes away too. So this is much simpler now, as sigma A is the stress concentration factor 1.72 times our bending stress, fully reversed, we had 35 as the sigma A. Those values squared, and then take the square root of that. So that gives you sigma A of 60.2 kpsi. You do the same thing for the sigma mean, except this time our bending stress, sigma m, equals 0, plus that sigma m from axial. We also have no axial stress, so that equals 0. So we won't have any of the axial portion. Instead, all we'll have is the shear portion. So KFS times R shear squared, and then that to 1/2. So we will simplify this a little bit. Sigma mean prime equals 3 times KFS, which we found to be 1.49, times our mean stress of 2.97 squared, and then take the square root of all of that. Plugging that in, you should get something close to a mean stress of 7.66 kpsi. So this is only a small addition to the stress value that we had before. So now we have an equivalent amplitude stress and equivalent mean stress, and we can plug these equivalents now into our factors of safety. So let's evaluate this with the Goodman equation. And if we do, we'll have 1 over NF equals sigma A prime over SE plus sigma M prime over SUT. Or in our situation, that works out to 60.2 over 29.5 plus 7.66 divided by 85. If you're wondering where this SE value came from, hopefully this is the same as when you solved the problem as 617. So you already solved the endurance strength, assuming it's bending. So recall, for these combined loadings, we assume bending, and then we fix that assumption on the axial stress by dividing by that 0.85. We didn't have any axial stress in this situation, so that didn't make too much of a difference. But our SE values you should have calculated when you did problem 617. All right, so if we do that, our calculated fatigue factor of safety is not high, 0.47, which means we are not expecting infinite life. Now, because this is less than 1, we will end up calculating cycles. But before we calculate cycles, since that is a little bit of mathematical work, if it's going to yield, it's not even going to last 1 cycle. So there's no point in calculating how many cycles it's going to last. So let's check that real quick. The yield strength the yield factor of safety as the yield strength, and we can combine these, the axial plus the mean, and come up with what we might call an equivalent maximum stress. So the strength compared to the maximum stress it's under. If you do that, you get 71 kpsi divided by 60.2 plus 7.66, so about 67.8, or a yield strength of about 1.5. All right. So now this says it's not going to yield, but it's really close. But the thing is, it's close, and we've included stress concentration factors inside those sigma A's and sigma M's. For yielding stress, we ought not to do that because the stress concentration factors don't affect the likelihood of a product to yield. or material to yield. So this is an overestimate of the stress, meaning that our 1.05 is a conservative estimate. In reality, it's probably a little higher than that. So as long as it's greater than 1, we don't need to go into any more detail. So we're going to say it will not yield, because our factor of safety against yielding is greater than 1. Now let's go back and figure out how many cycles. To look at the cycles, we need to first convert our current stress situation to an equivalent fully reversed stress. So before, we had a fully reversed stress of 35, and we didn't have any mean stress, but now we do have a mean stress constantly. So to equivalent fully reversed stress is just flipping around the Goodman equation and solving for SE. So what that ends up setting n equal to 1 and solving for SE, calling that your equivalent fully reversed stress. So what you get is sigma m over the ultimate strength. So if we plug those in, we get 60.2 divided by 1 minus sigma m is 7.66, and the ultimate strength from the back of the book is that. All of that is equivalent to 66.2 kpsi. Now notice that's quite a bit higher than our fully reversed stress of 35 kpsi that we found before. So that mean stress does add quite a bit to the effect of the stress. All right, based on the ultimate strength, we can look at figure 618 and figure out an F value. So if we look at figure 618 and trace by the ultimate strength of 85 kpsi, you should come up with a value pretty close to 0.9, so 0.867 in this case. It's a little overly precise. Your values, again, looking at a graph, may be slightly different. You could also calculate that as well using the equations. We'll also need our A values and our B values. These are what we've seen before, F, the ratio F times the ultimate strength over our endurance strength squared. And B is negative 1/3 the log of that piece. F times the ultimate strength over the endurance strength. So for our situations, we have, just plugging in numbers here, 0.867 times our ultimate strength of 85 kpsi. That is squared. And then our endurance strength, which we found from before when we did this problem in 617, was 29.5. So A for this problem will be about 184.1. This is kpsi over kpsi. Excuse me, kpsi squared over kpsi. So we end up with kpsi as the units. And B would be negative 1/3 log and 0.867. These numbers are the exact same, 85 and 29.5. And since this is kpsi over kpsi and it's a log value, we end up with just a number here, negative 0.1325. All right, finally the last step, we can calculate the number of cycles as the fully reversed stress. This is the line fit for the SN curve over A, and 1 over B. For our situation, plugging in all the values, we have 66.2 divided by A, which is 184.1 kpsi. kpsi over kpsi here, so we should have unitless again. 1 over negative 0.1325. All right, so finally, we can calculate the number of cycles we'd expect to see as a fairly low 2,300 cycles, which is what we would expect considering the stress is fairly high. Now you can go back to 617 and compare that to the values that you found from before. Alright, so in this problem, we've taken the combined loading approach, which is that anytime we have more than one type of loading, including if it doesn't have bending at all, we're going to assume bending because it makes the equations just that much easier. So in this problem we had bending, and then now we've added torsion to it. So finding our SE values would be exactly the same as 617. We assumed bending for that, and that's what it was, meaning that Kc was 1. We need to find stress concentration factors for both bending and torsion and apply those to the stress values. And then use the von Mises forms of the equation. That is the Kf's times the sigma A's for each type of loading, or the amplitude stresses for each type of loading. The sigma M's would be the same thing, the stress concentration factors times the means for each stress of each type of loading. That gives us our sigma A von Mises and sigma M von Mises. We can put that in the equivalent Goodman equation and come up with the factor of safety. Always check for yielding. And then if NF is less than 1, we apply our estimate, our line fit for a fully reversed cycles of loading compared to stress. And what we end up with is calculating the number of cycles. So that does it for this problem. Until next time.